a lot of times when we're given a bunch of data, like in a table or something, we can look at that information and all of a sudden glean from it a pattern. And that pattern quite often will allow us to produce a general formulation for the pattern we're seeing. So we can not only predict the next thing on the table, but any subsequent thing on the table that we want. When that happens, that's a great moment because it means that we really understand what we're given. Let me show you some examples, and let's see if we can actually find the pattern. So here's a table. This is a table of two people's ages. There's Bella's age and Martha's age for various years. So you can see when Bella was 5, Martha was 3. When Bella was 6, Martha was 4. Not surprising because a year later, she's a year older and Martha's a year older. Similarly, when Bella turned 7, Martha turned 5. Now, do we see a pattern here? Well, what I see here is that it's always the case that Bella is 2 years older than Martha. If I take Martha's age and add 2, I get Bella's age. Or, the other way around, if I take Bella's age and subtract 2, I get Martha's age. Is that really true? Sure. Take 6 and subtract 2, I get 4. That's cool? You take 7, subtract 2, I get 5. There's a pattern here. If you take Bella's age and subtract 2, you're going to actually get Martha's age. So now here's the big finish. The big finish is, suppose that we just say that Bella's age is n. Now n's not a number, but we're thinking about it as an unknown. It's some number and we just don't know what it is. It's unspecified. But I'll tell you something. If Bella's age is n, I think you know how old Martha is. What would Martha's age be? Well, when Bella is 5, Martha is 2 years younger than that. So 5 minus 2. When Bella is 6, Martha is 6 minus 2. When Bella is 7, Martha is 7 minus 2. When Bella is n, Martha's going to be n minus 2. And we've now created an algebraic expression that captures Martha's age in terms of Bella's age. So if someone says, hey, Bella is 16, we can actually immediately say what Martha's age is going to be. We just plug in 16 for n, and we see 16 minus 2, or we see 14. Very, very cool. That is the power of finding a formula, finding a pattern in a table of data. Here's one. So a number of years, and then the corresponding number of decades. So a decade, remember, happens every 10 years. So 10 years we have 1 decade, 20 years we have 2 decades, 30 years we have 3 decades, 40 years we have 4 decades. What if I have Y number of years? How many decades does that correspond to? Well, let's see if we can actually write down an expression that captures that. Well, let's see. How do we go from 10 to 1 that also works going from 20 to 2? Well, let's see. To go from 10 to 1, if I divide by 10, I get 1. If I take 20 and divide by 10 again, I get 2. If I take 30 and divide by 10, I get 3. If I take 40 and divide by 10, I get 4. If I take Y, what should I do? I should divide by 10. So I should take Y divided by 10. Y divided by 10. So check it out. If I had 50 years, that would correspond to 50 divided by 10, which would be 5 decades. And that's correct. So you can see we generated an algebraic expression that generalizes all the data from our table. Now that is pretty neat. And that's the power of mathematics. Going from what we know, take off into a general situation that allows us to see the structure. Very cool.